but I am now. All right. So it's actually a very important piece of information when you're trying to deduce a structure, especially if you have other data like NMR data and infrared and so on and so forth, and you're trying to deduce a structure for a compound. So the way that you do it is HREF minus what?
H mole.
H molecule divided by 2. Is that right?
Yes.
All right. So HREF, this is standard. HREF is always going to be 2N plus 2, where N is the number of carbons. Sorry about that. My little pen's acting up. Where N is the number of carbons. And then H molecule is actually what's present in the molecule, right? So the subscript number by the H, that's H molecule. So all of these have C something, H something, right? And so when we apply this, right, you're gonna get a whole number. It's either gonna be somewhere between 0 and infinity, right? But most of the times you never get infinity. But it's just, the point is it's gonna be a whole number. It's not gonna be a fraction. It can't be a fraction. All right. So for A, what is N for A?
2.
2, right? So if we apply that, so 2N plus 2 is what? 6.
6.
Right? And so 6 is HREF for that first example. And then H molecule is what? How many hydrogens are present there?
2.
2. So if I go over here and I plug those numbers into this equation, HREF is 6, H molecule is 2, right? So 6 minus 2 over 2 is 2. Is that right? Yes or no?
Yes.
Yeah, it's 2, right? It's very, very simple. And so now what that means is that compound A has 2 degrees of unsaturation. Right? There's another term or another phrase we say, the index of hydrogen deficiency, IHD. It's the same, it's interchangeable. But we got 2 degrees of unsaturation. What does that mean? It means that we can have what? 2 double bonds or what?
2 rings.
2 rings or 1 ring and 1 double bond, so on and so forth. So for that one, since it only has 2 carbons, there's no way you can have 2 rings, right? But there is a way that you can have 2 double bonds. So that C2H2 right? An example of that would be an alkyne, right? You got 2 pi bonds in there. Is that right? Because that triple bond is made up of what? A sigma bond and what? 2 pi bonds. Is that right?
Yes.
Yeah. So that if you were to propose a structure for that molecular formula, that's what you would have, right? That's the structure that you could propose. But you're not going to get 2 rings because you don't have enough carbons. All right, let's look at B. I want to do B also. B is C6H6. So what is HREF for B?
C6H14.
Right. So N is the number of carbons, so that's going to be 6. HREF is going to be 14. That's right. And then what about the H molecule? What's present?
6.
6, right? H molecule is always going to be that subscripted number. So what is that, 4? Is that right?
Yeah.
So this has, I'm gonna abbreviate this as IHD. IHD is 4. All right, and so now that means that you can have what? 3 rings and 1 double bond, 3 double bonds and 1 ring, 2 rings and 2 double bonds, so on and so forth. So because it's C6H6, if we had to propose a structure for that, one structure that's plausible is a ring with 6 carbons. I should have cut that. Let me add a page right quick. All right, so for C6, we said that the IHD was 4, the index of hydrogen deficiency. It's the same thing. Let me go ahead and put that in. Because some books have it listed as IHD. Some books say degrees of unsaturation. It's all the same. Right, it's 4. So we said that if we had a ring with 6 carbons in it, right, and we put 3 double bonds in that ring, that would satisfy that, wouldn't it? Because the ring is a degree of unsaturation, and then each pi bond is a degree of unsaturation. So that's a total of 1 ring and 3 excuse me, 3 pi bonds, which totals up to 4. Is that right?
Yes, that's right.
All right.
Did he do it?
All right. Let's do.
I'm about to go get the blankets. I bet.
All right. Let's do. Let me just cut them right quick. We'll do E and F real quick, because this right here is not rocket science. I'd much rather be doing a reaction, but I don't want to. I'm not in a rush, and I want to make sure you get it, because you are going to see it again. All right. So these 2 examples right here, right? One has a halogen present, one has a nitrogen present. Sometimes, depending on what book you're using, they'll give you a different method. For me, if you have a halogen, what do you have to do?
Subtract 1 for every halogen you have.
And which number? Href or H molecule?
Href.
Good. So each halogen, you're going to subtract 1 from Href. All right. And then for nitrogen, you're going to add 1 to Href. Any group 5 atom, nitrogen, phosphorus, anything in that group. So for each nitrogen. All right. Oh, let me close this door. 1 second. All right, so let's calculate Href for E. What is it? So href is always going to be the same. 2 times n plus 2, right? Where n is the number of carbons. So this is going to be 2 times 7 plus 2, which is what? 16? Is that right?
Yeah.
All right. So 2 times 7 plus 2, 16. And then H molecule is 11. You can see right away when you subtract those two and try to divide by 2, it's going to give you, it's not going to give you a whole number, right? So now we need to subtract 1 from href. So because of bromine, so that's minus 1. So that'll be 15. So then in your equation, it'll be 15 minus 11 over 2, which is 2. Yes or no?
Yes.
Yep.
Right. So if you had to propose a structure for C7, H11, Br, and the degrees of unsaturation are 2, you got 2 choices. In my opinion, I think the easiest way to think about it is the first choice would be a 7-carbon chain, right? So 6 strokes. If you draw it in skeletal form, it's always 1 less stroke, right? So if you got 7 carbons, it's 6 strokes, 6 carbons, 5 strokes, so on and so forth. And then we can stick in a double bond here and here. You can put bromine anywhere. It doesn't matter. So if we count up, we got 7 carbons. This is a CH3. This is a CH2. It's terminal, right? There's a 1 hydrogen there. And there's a hydrogen on each one of these. Boom. So let's count them up. So that's 3 hydrogens, 4, 5, 6, 7, 8 hydrogens. And then I got 2 hydrogens here. That's 9, 10 hydrogens. Am I right? And then I have 1 here. So that's a total of 11 hydrogens. So C7H11Br. That's an example of a structure that you could propose. Right? And any structure you propose got to be a proper Lewis form. Can't have 5 bonds to carbon and all that crazy stuff. Or if you want one of your degrees of unsaturation to be a ring, you could draw a 7-membered ring like that. Stick a double bond somewhere in that ring, and then put a bromine on the ring. Doesn't matter where, and then boom, it's going to match. It's going to be C7H11Br. You got to.
Dr.
Yes.
On the exam, would we be like I'm required to like draw like possible structures from what we're getting from the degrees of saturation?
Yeah.
Okay.
You should have enough experience at this point to at least be able to propose a chain, a skeletal structure, or you can draw it out in Lewis form. It doesn't matter to me, but you got enough experience with drawing structures at this point that you should be able to draw out a 7-carbon chain and put a double bond somewhere in there, or however many double bonds you need. So,
okay.
Yeah. Good question. So that's two hydrogens there, and every other carbon has 2. Except for the one where bromine is. All right, so that should be 11, is that right? 2, 4, 6, 8, 9, 10, 11. Right, so that's an idea of how to take the degrees of unsaturation and then apply it, right? You figure out the degrees of unsaturation, and then you can propose a structure based on it. But the structure has to be a valid Lewis structure. It cannot have like octet violations in it or something like that. My suggestion is if you have a molecule or you have a molecular formula that gives you more than 1 degree of unsaturation, my suggestion is to take one of those degrees and make it a ring, and then the rest of them you can think about adding double bonds within the ring, or just draw it out as a straight chain and then put as many double bonds in that you need to meet your degrees of unsaturation. All right, are y'all following it?
Can you recount the hydrogens for the skeletal form of the first one, please?
Yeah, let's do it. So you got 2 here, is that right?
Yes.
That's 3, because this carbon right here that's in the alkene, that's a carbon right there. It's only gonna have 1 bond to it because it's got a double bond and then it's got another bond, the carbon on the other side. So that's 3, that's 4, 5, 6, 7, 8, and then 11.
Okay, thank you.
Same over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Even though my hydrogens look like crackheads, you get the point. Yours probably don't. All right.
Yes, thank you.
Okay. All right. Any other questions about that? Let's do the last one. That's a little bit more challenging. C5H9N. I got to add another page. All right. So C5H9N. Again, that looks like a 4. Sorry. With the degrees of unsaturation, if I have a nitrogen present, I need to make sure that I account for that by adding 1 to HREF. So HREF is going to be 2 times 5 plus 2, which is going to be 12. Is that right? You can see right away when you subtract H molecule from that, it's going to be 3 over 2. So that'll give you a fraction, and it can't be a fraction. So this should be plus 1 because of the nitrogen. So that's 13. And then H molecule is 9, so we put that in. 13 minus 9 over 2, which is 2. Yes or no?
Yeah, that's good.
All right, thank you. All right, so if that's the case, let's propose a structure. So you got 2 degrees of unsaturation. So again, the easiest approach is to draw you out a 5-carbon chain, like so. And it's got 2 degrees of unsaturation, so you need 2 double bonds in there, or 2 pi bonds, right? And then on this end, I'm going to add in my nitrogen. And then, of course, nitrogen is neutral. I'm going to put 2 hydrogens on that, right? And then everywhere else, I'm going to put in my hydrogens. Let's see. 1 second. All right, so that's that. And I'm gonna add a hydrogen here. And then here. And then 2 here. Does that match the formula? C5H9N. Yeah, so let's count them up. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, no, maybe.
Yes.
Yes.
We have a 5-member ring also, right? Because the degrees of unsaturation is rings and or double bonds. Is that right? So we could also or pi bonds. Let me quit saying double bonds. Right, so we can also think about a 5-member ring like this. Not that ugly though. Following? So now with this match, I'll put a hydrogen here, 2 hydrogens on this carbon, 2 here. And then how many on each carbon in a double bond? I just want to see how you're thinking.
1.
1.
1 on each one, good. Sorry about that. So here. And then 1 here. Is that 9 total? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so that both of those structures would suffice. But the easiest way, in my opinion, is to just do a chain, and then from that chain you add in is the pi bonds that you need. All right, let's go back up to. Is anybody still writing that down? By the way, before I move to something else. So when you're doing degrees of unsaturation, when you have a molecular formula, you may have to propose a structure for that formula, right? So you always do degrees of unsaturation first so that you'll know what's available to you. How many pi bonds can I put in? Or how many rings can it be? All right, let's go back to here. Do a little bit more nomenclature. So with any compound, you always want to find the longest continuous chain, right? That's your goal. That's one of your goals anyway. Let me go ahead and add a page down here because I don't want to have to squeeze this in here. All right, so I'm gonna cut this. I'll cut both of these. So I'll cut the whole question because it asks you to give Iupac names, right? So that little acronym Iupac is International Union of Pure and Applied Chemistry. That's what that means. So it's a group of scientists, and they kind of set the rules for different conventions in the chemical sciences, right? So one of the things that had to be set, you had to have a set way of naming stuff. You can't have 5 or 6 different ways to name a compound. So you have to have a set of rules. And then of course, within that set of rules, you'll have some exceptions. So the first thing you want to do here is to find the longest chain. Right? And that's fine, but then sometimes you have other functional groups that are present. So you have to find the longest chain that contains whatever your functional group is that you are thinking about, right? So containing the functional group. Right, so whatever the longest, in this case, the functional group that we're dealing with is an alkene. So we want to find that longest chain, right? So we can start counting. Actually, for this structure, it's like 3 different ways you can count to find the longest chain. So let's just start here. Let's take the easy way. 1, 2, hold up, I need to make that a little smaller. So let's say 1, 2, 3, 4, 5, 6, 7. So that chain is 7 carbons. You agree?
Yeah.
All right, let's take a different route. We're gonna start the same end, 3, 4, 5, 6, 7, 8. That chain has 8 carbons. Anybody not see that? All right, so that chain has 8 carbons. And then if you count, just for the sake of argument, count from the carbon that's pointed up top, 1, 2, 3, 4, 5, 6, 7, 8. You come to the same conclusion. So that the 8 carbon chain is your longest carbon chain that contains your alkene. Following? Yes or no?
Yes.
Yeah.
So you got 8 carbons in that chain. So I'm going to erase all these highlighted. I like the blue, so I'm gonna come back with that. So hold up. It's not a radical. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we got our longest chain is 8. What's the parent going to be? If it's 8 carbons, what's the Greek prefix for 8?
Octa.
Yeah, octa. So it's going to be octene, right? Because of the double bond. So we already know for this, the parent is going to be octene. Oct because it's 8 carbons, ene because there's a double bond present. Anybody disagree with that?
No.
All right. So octene is my parent. Now we need to set about figuring out where the double bond is, because we gotta give that double bond an address, and we gotta figure out if there's any other things attached to that chain. So if the 8 carbon chain is outlined in blue, are there any other substituents attached to the chain that you can see? Right? Are these 2 carbons over here a part of that longest chain?
No.
No. What about this methyl group right here?
Nope.
No. So those 2 groups are substituents. So this is a substituent, and then this is a substituent. Following? A substituent is anything that's not a part of the that's attached to the longest chain.
Wait, why do we decide to count from the top one if we said the left one, they were the same number across?
That's just the one I like.
Okay.
There's no, you could have counted from either, we could have counted from either one of them.
Okay.
Yeah. You want to change it?
No.
You sure? I can change it.
Mm-mm.
Just leave it.
Yeah.
Okay. All right. We're going to leave it. So now I got 2 substituents. I need to figure out what they are. Right. So let me zoom in on that. So that at the end of that line right there, that is I'll write that over up here. This is a CH3. Is that right? Yes or no?
Yes.
All right. And then on the other side, this is you can't really see it, tell it because it's in skeletal form, but it's a CH2. Oh, sorry, wrong pen. This is a CH2, CH3. Right? Anybody disagree with that? This vertex right here is a CH2, and the end of that line is a CH3. We good with that?
Yes.
Yeah.
All right. And so that group, that CH2, CH3, that's a 2 carbon chain attached to your longest chain. under normal circumstances, we would call that ethane. But because it's attached to the chain as a substituent, we're going to change the suffix. So instead of it being ethane, this now becomes an ethyl group, right? Ethyl. We change that suffix. That when you see it, when it ends in YL, then what that indicates is that it's a substituent and it's not just independent. If you see ethane, that means it's independent, right? So instead of it being a CH2, CH3, it'll be CH3 bonded to another CH3. But when you pull off a hydrogen and stick it on as a substituent, it becomes an ethyl group, right? Ethane would look like this. It would be CH3 bonded to another CH3. Well, obviously you can't attach that because both carbons have a full octet. So in order to attach it as a substituent, you change it, take off one of the hydrogens, and now on this carbon, you can attach it as a substituent. All right, and then on the other side, this is a CH3. Normally it would be methane, but because it's attached, we call it methyl. Right, again, change the suffix. Ane goes to ill, that means it goes from being independent to being a substituent. We okay with that?
So Dr. Russell,
Yes.
you said if it ends with ill, it's basically a substituent and it's not dependent.
Yeah, it's attached to something.
And then if it's aim, if it ends with aim, it's not dependent.
Right.
Okay.
Right. All right. So let's look at it. We got enough information now to put the name together. So we found the longest chain, which is 8 carbons. We said the parent was octene. I was right. I'm going to put that down here. I don't want to jumble it up. All right. We know what the substituents are and where they are because we're going to start counting from which end. Keep in mind, this is an alkane. So where are we going to start counting from?
That alkene starts to form.
Say again.
Where the alkene starts to form.
Yeah, the closest end to that, to the major functional group. So we're going to start counting here. 1, 2, 3, 4, 5, 6, 7, 8. That okay? So where is your alkene and where are your substituents? Which carbons? You got it.
Alkene.
Go ahead. Say that again. You kind of chopped up.
The alkene is between 2 and 3, right?
Good, good. That's right. What about your substituents?
They're,
2. You got it. The methyl group is at 2, right?
Yes.
And then where's the ethyl group?
Is it 5?
Yes, it's attached to 5. That's right. Yep. So now we can construct this name. And then we're going to put the stereochemistry in too, because y'all smart like that. We're going to just put it all in together. So the location of the double bond is between 2 and 3. Let me move this over because I remember running out of room with my sloppy handwriting. Right? So we put that number here, right? 2 octene. Is that right?
Yes.
That's telling me that in that 8 carbon chain, the double bond starts at carbon 2, and it's the other carbon involved in it is 3, but we give it the lowest number, so it's 2 octene. Again, the ene is the suffix. That means there's a double bond present. The oct is the parent, right? Tells us how many carbons in the chain. All right, now we need to put the substituents in. Is that right? Because that's how you construct the name. The parent is the street, the substituents are the residents, and the numbers with the substituents are the addresses. So the methyl lives at carbon 2, the ethyl lives at carbon 5. But when you list them in alphabetical order, regardless of the number in front of them. So this is going to be what? 5 ethyl, is that right? Because E comes before M, right, in the alphabet.
Yes.
And then what, 2 methyl? 2 octane. 5 ethyl, 2 methyl, 2 octane. Anybody not okay with that?
What's the difference between you wrote ethane and ethyl right there?
Yeah, the ethane is independent. It's this. It's just a 2 carbon chain, right? It's not attached to anything. But when I attach it as a substituent, I have to take off one of those hydrogens so that I can fit something else on there. Then it becomes a substituent. So I change the suffix from ane to ill.
Okay.
You see it?
Yep.
All right.
Dr. Russell,
Go ahead.
can you tell me how you got 5 and 2 and 2?
Yeah, sure. So the 5 comes from again, you got an 8 carbon chain, right? That's the street. And then everything that lives on that chain, every substituent, has to have an address. So on carbon number 5 up here, can you see that? I know it's kind of messy, but carbon 5 right here, that's where that ethyl group is attached.
Okay.
So the address for that group is 5. So I got to put the address and the resident together. So it's 5 ethyl.
Okay.
And then over on carbon 2, right here, that second carbon, I'll have a methyl group attached to it. So that's where the 2 came from in front of the methyl group, because that's the location. It's on the second carbon in the chain. Yes or no?
Yes.
Okay, and then the double bond is between 2 and 3, right? So the location can be 2 or 3, but I give it the lowest number possible. So that's why I gave it the number 2.
Okay, thank you.
Yeah, when we look at the whole name, it's 5 ethyl, 2 methyl, 2 octane. Again, this is the parent. This is the suffix, which the suffix is going to tell me what functional groups are present. Is it a alkene? Is it an alkane? Is it an alkyne, which is a triple bond? And then these are your residents. Right, the proper name is substituents, but I like to try to make it more colloquial. Right? And then these are the locations of your substituents. In relation to that longest chain, right? What are we missing? We're missing something. One thing. We talked about it Monday.
The trans or the cis.
Who is that?
Kristen.
Okay, then you're right. Is it trans or is it cis or is it E or is it Z, or can we not determine it?
Yeah, determine, right?
You can't determine it because
It's like,
go ahead.
terminal something. That's how I know we can't do it.
Well, no, it's not terminal, but it's got the same substituent twice on the alkene. So you won't be able to determine. It's tri-substituted overall. Can you see that? that is tri-substituted because you got a, let me see if I can find a different color. You got a carbon here, and one here attached to the alkene itself. So it's tri-substituted, but two of those groups are the same on the left side. So you won't be able to prioritize it, right? Because remember, trans, cis, and trans is for disubstituted, and then E and Z is for tri-substituted and tetra. But you can't assign priority because both of your groups are carbon. So we have to leave it how it is. Does that make sense?
Yes.
Yeah, because remember, if it's tri-substituted, we got to do E and Z. But in order to do E and Z, you have to be able to assign priority to the groups that are attached, high and low. Remember that from Monday?
Okay, yeah, makes sense now.
Yeah, but since it's tri-substituted, but two of the groups are identical, then you can't do it. Now, if one of those methyl groups was on 3, then we could do it. We could say if it was E or Z. But you were right, Kristen, in thinking about it's the stereochemistry that was missing, but we can't do it here. All right, any questions about anything so far? Man, time is just flying by, man. 11:51. All right. Let's see if we can do the next one. Somebody help me on that one. I'm gonna cut it and put it somewhere else because it's getting messy. Actually, I'm just gonna draw it. How many carbons is that? 1, 2, 6. I'm just gonna draw it down here. Okay, I'm right. One. Let me see. Okay. Yeah, I think that's right. Or do I have an extra carbon in here? I think I got an extra carbon right there. You know what? Let's just redraw it. Let me scroll back up to the top. We can fix that. All right. So now we're gonna look at this one, and then this will be the last thing we do because we're almost out of time. So what's the first thing we got to do?
Find the longest
Okay.
chain.
Find the longest chain that contains the functional group. Is that right?
Yep.
My screen is frozen. Let me stop it and then reshare. All right. So again, since we're working with an alkene, The longest chain has to contain that. And the alkene cannot be the substituent. So we're going to start numbering since it's terminal here, 1 and 2. Right? If we go to the right, the longest chain is going to be 4 carbons. If we go to the left, the longest chain is going to be 5 carbons. Are you following that?
Yeah.
Mhm.
All right. So my longest chain is 5 carbons. Anybody disagree?
Oh,
So let me highlight them like we did the last time. I think that'll help. So 1, 2, 3, 4, 5. Right? So what's attached to that chain? How many, what substituents do we have? Well, first of all, what's the parent going to be?
Pentene.
Pentene, good. Ene, pent for 5 carbons, and then where is it located?
what?
We call it 1-pentene. All right, it's in between 1 and 2. Give the lowest number, the alkene is. All right, so now let's look at the substituents. We got a CH3 here. And let me let me help somebody with this because this is a common mistake. This is also a CH3, right? But because it's in the longest chain, it is not a methyl. People they get that confused all the time. If it's part of the longest chain, it's not a substituent. So you don't have to call it a methyl group, right? It's just a carbon in the chain. But this CH3 is a methyl, right? Because it's on the longest chain, not in it. All right, and then on the other side, you have a 3-carbon chain right here, right? Now, under normal circumstances, so let me just give you that. So for 3 carbons, right, that'll be propane, right? If it's a 3-carbon substituent, what would it be?
Me?
Propyl, right?
No.
But that would be if it was attached at the first carbon in the chain. This is a little bit different. Here, the 3-carbon chain is attached by that middle carbon. So there's a special name for this group. It's called an isopropyl. Right? Isopropyl. All right. So and that's isopropyl because of the way that 3-carbon chain is attached to your longest chain. Right? It's attached at the middle carbon of the propane chain, so we call it isopropyl. All right, so you think we could put the name together now? There's no stereochemistry because it's a terminal alkene. So can we put the name together now?
Yeah.
All right, let's name it. What's the location of the methyl?
4.
And then the location of the isopropyl is where? It's at 2, right?
Yeah, 2.
All right. So then I comes before M. Is that right?
Yes.
So 2 isopropyl. What? 4-methyl. 1-pentene. Always want to put that ene on the end to indicate that there's a double bond present. Right? Any questions about that? About the naming? I know it's long and it's a pretty arduous process, to be honest with you. That's why I hate nomenclature. A lot of rules and a lot of conventions that you have to follow for nomenclature, but it is what it is.
Dr. Russell, can you explain the ISO thing
Yeah,
again?
yeah. So let me I'll do it down here. So normally, if you have a 3-carbon chain, right, like that, and it's attached to something as a substituent. Well, let me. So these 3 carbons right here are attached to some bigger unit, right? Then this would be a propyl substituent, right? Like if I have a 15 carbon chain or 10 carbon chain, and the propyl is somewhere like that, then the 3 carbons that are here would just be a propyl group and not anything else. It's just 3 carbons. Normally it would be propane, but because it's a substituent, it's propyl. But when you attach it at the middle carbon of the propane chain, right? So instead of being attached like that, it's attached like this. Then that's when we call it isopropyl, right? Because what the iso part is kind of it's kind of shorthand for isomer, right? So iso meaning that it is an isomer of propane. So, that's because it's attached at a different carbon. So instead of being just propyl, now it's isopropyl. The propyl tells you it's 3 carbons. The iso tells you that it's not attached to the first carbon, but to the second carbon, the middle carbon, between the other 2 carbons.
All right, thank you.
Mm-hmm. All right, any other questions? We're 2 minutes over time, so I'm gonna